known as categorical, also known as non-metric measurement, and continuous, known as metric measurement. You might be aware that there are four kinds of measurements: nominal, ordinal, interval, and ratio. Nominal and ordinal are categorical measurements, whereas interval and ratio are continuous or metric measurements. Why I am discussing this? Because this provides a base for deciding on which statistical test to perform. This provides a base. Because unless you don't know what kind of measurement you have used while collecting the data, reaching out to a statistical test is pretty difficult. Let me show you how. So this is a decision tree that we make. Let's say if we have to decide on whether we should go for a Pearson correlation or for a Spearman correlation. Then first step is whether the data has been taken on a metric measurement or categorical measurement. If it is categorical measurement, then it will violate the assumptions of normality, because categorical data won't be normally distributed. So if you have collected any data which is categorical, that is either on a nominal scale or ordinal scale, then directly move on to, and particularly in case of ordinal measurements, directly move on to Spearman rank correlation. No need to test for other assumptions. But if you have taken a metric data, then first you need to check its normality distribution. So Shapiro will test. There are many tests for normality: histogram, Shapiro will, Kolmogorov-Smirnov, but Shapiro will is the most powerful test. If it violates the assumptions of normality, again you have to go for Spearman correlation. But if it passes the test of normality, then again you have to see that your sample size is small or big. If you have a small sample size, again you have to go for Spearman correlation. If a large sample size, then go for Pearson correlation. That's how we decide on. But what is this correlation? This correlation is actually the association between two variables. Henceforth, I will use the terms X and Y, where X means independent variable and Y means dependent variable. So a change in X, if it brings a change in Y, then we say that they are correlated. For example, let's take a very trivial example of an air conditioner in your room. The more, or a fan with a regulator. So the speed of the fan is dependent on the regulator. Let's say you have moved regulator from knob number 2 to number 3. It will increase the speed of the fan. So they are correlated. If you decrease the knob from 3 to 2 or from 4 to 3, it will decrease the speed of the fan also. Again, this is something which is correlated. This correlation in its unstandardized form is known as covariance. Now, what is covariance? When you are measuring simultaneously two or more variances. Now, what is variance? Anything, any value, if it moves beyond its mean value or standardized value, that is known as variance. So let's say you are bringing a change in X. That means you are moving it from its mean value. And simultaneously you are measuring the variance in Y. So both these two variances, when you are measuring, they are known as, simultaneously measuring two variances, they are known as covariance. This is the unstandardized form. The standardized form of this covariance is known as correlation. This correlation ranges from -1 to +1 or -100% to +100%. Now, I've, I've placed before you three examples. Now, if you see, these are scatter plots. The basic visualization of correlation is done with the help of scatter plots. If you see the situation 1, as there is an increase in the variable 1, you can see variable 2 is decreasing. This is a negative correlation. In second situation, R is 0. That is, there is no correlation between V1 and V2. Means if you change V1, there won't be any effect of V2. The third situation is, as V1 increases, V2 also increases. The variable 1 increases, variable 2 also increases. And this increase in the first and the third case, the first case is -0.90, and in the third case it's +0.90. So we should not say that the negative sign, due to the negative sign, it's a weak correlation. No, the first case is also a case of strong correlation and is the equivalent to the third case. Only thing is that the plus and minus signs, they don't show the magnitude of the correlation, they show the direction of the correlation. So let's say you are bringing a change in X, which is causing a negative change in Y. Means if X is increased, Y is decreasing, or vice versa. If X is decreasing, Y is increasing. Means both variances are happening in opposite direction. Means both are moving in opposite direction. Then that is known as a negative correlation. If the variances are moving in the same direction, means increasing X leads to increase in Y, or decreasing X leads to decrease in Y, then in that case, it is a positive correlation. How much change in X is leading to change in Y, that is known as the correlation coefficient, or the degree of association, or the degree of correlation. So in our first case, there is 90%, 0.9, 90% negative correlation. In the third case, there is a 90% positive correlation. That simply means if V1 is increased by 1%, sorry, if V1 is increased by 100%, it will bring 90% decrease in variable 2. In third case, if V1 is increased by 90%, 100%, it will bring 90% increase in V2. It will cause 90% increase in V2 and vice versa. So I hope the basic concept of covariance and correlation is clear to you. The hypothesis that we formulate in case of correlations is that the null hypothesis says that the population correlation coefficient is 0. That means there is no significant association between both the variables that you are measuring. The alternate hypothesis says that the population correlation coefficient is not equal to 0, means there exists some significant correlation. This is the case of two-tailed test. Two-tailed test means when you are not, two-tailed hypothesis or two-tailed test means when you are not sure whether the correlation exists or does not exist. And if it exists, what kind of correlation is. When you are sure, then you can formulate one-tailed significance test, one-tailed hypothesis, that absolutely the population correlation coefficient will be 0. Or if it is not 0, then it can be either greater than 0 or less than 0. Greater than zero means positive correlation. Less than zero means on the negative side, negative correlation. If you are sure about it, then you should frame one-tailed hypothesis. Otherwise, you should go for two-tailed hypothesis. Like I'm sure that if I decrease the temperature on the remote of my air conditioner from 25 to 23, the time taken for the room to cool will be less. Let's say the room will cool in less time. Now, this is something, a positive correlation. I'm sure about it. This is going to happen. So I will say that the population correlation coefficient is greater than zero. There is a positive correlation. If opposite is happening, then there will be a negative correlation. So that's the theory behind the correlation. Now, let's do the hands-on. So for that matter, I have shared with you the data sets. Are the data sets with you people?
Yes, sir, we have the data set.
Okay, so please open the first data set, that is correlation data set 1. You can go to file, open, data, and select this data wherever you have saved. Now here we will focus on three variables: revise, exam, and anxiety. So the first variable is about time spent revising a course. This is the exam performance of the student, means the absolute numbers that they have got, the percentage. And this is the score of their anxiety level when they were tested about their anxiety level. Then this is the score of the anxiety. I want to know that what is the association between anxiety and exam performance? Is there any association between exam anxiety and exam performance? Will increase in anxiety lead to decrease in exam performance or vice versa? What is the situation? So for that matter, I will do a correlation test. But now the question is which type of correlation? So here you can see that your exam anxiety is on a absolute numbers, percentage, absolute numbers. So this is a metric measurement. It's taken on a interval scale. This anxiety is again absolute numbers taken on a ratio scale. So both are continuous measurements. If both are continuous measurements, both your variables among whom you are trying to test the association, if both are continuous measurement, then we should go with Pearson correlation, which is also known as Pearson product moment correlation. You can do these two at once, or if you want to put the revision time, because this is also taken on an interval scale, you can take this also, three at once. But for more clarity, first I will try to test the association between exam performance and anxiety. So first, let's have a look, initial look on how they are correlated and whether they are correlated or not. So for preliminary examination of any data, the best way is the visualization. So correlations, as I told, are tested or visualized through scatter plots. So you can go to graph, legacy dialogues, and here you will find an option of scatter dot. Select this simple scatter, and on the x-axis take exam anxiety, because we are measuring The effect of exam anxiety on performance, and on y-axis take exam performance, and click OK. You will get this scatter plot. But as of now, this scatter plot is not telling you, means it's not that much clear. So what we will do, if you see, it is showing that there is, as exam anxiety increases, exam performance decreases. But to be more clear, let's fit it on a straight line. Let's make a linear association. So double click on this, and here you will find add fit line at total. Click on this, close, close, and now you can see the straight line is going downwards. Means as exam anxiety increases, exam performance decreases. So there seems to be a correlation between exam anxiety and exam performance. And there is a negative correlation. But what is the magnitude of this correlation? So initially through scatter plot, we came to know that yes, there is a correlation. There is a negative correlation. But again, the question is that what is the magnitude? So initial observation scatter plot has told us. Now we will go to analyze, and then we will go to correlate. It's a bivariate correlation. So we'll click on bivariate, and we will take the exam performance and exam anxiety. Here you are presented with the option of using Pearson, Cantel-Dow, and Spearman. Since our both the data are continuous measurements, so we will take Pearson correlation. And for better interpretability, we will keep two-tailed. In options, you have to do nothing. Nothing. Simply click on it. And now see this way. This way. Theoretical. If you see this value, it is showing minus 0.441. That means uh, exam anxiety and exam performance are negatively correlated with each other, and the correlation coefficient is 0.441, means 44.1%. And correlation is always classified as weak correlation, moderate correlation, strong correlation, and very high correlation. So correlation ranging from 1 to 25% is weak correlation. 26 to 50% is moderate correlation. 51 to 75% is strong correlation. And greater than 75%. And it cannot go beyond 100%. And 100% is an ideal situation. That ideal situation you won't get. So 75%, greater than 75% is very high correlation. Now see this. Minus 44.1%. Because it's minus 0.441, if you convert it into percentage, it is minus 44.1%. And this, whether this is significant or not, there might be a correlation, but whether it is statistically significant or not, this p-value will tell. So you might be knowing that if p-value is less than 0.05 or 5%, then we say that the statistical calculation that we are doing is significant. If it is greater than 0.05 or greater than 5%, then we say that the statistical computation that we have done is non-significant. Means there might be a value, but it is of no use. It's not significant. But if it is less than 0.05, then whether it's a small value or a big value, it makes a difference. It is significant. So we have found that there is a negative correlation between exam anxiety and performance, and it is 44.1%. So moderate correlation. So we have a negative and moderate correlation, and which is also statistically significant. So we will write the results from the scatter plot. We found that there, there exists a negative correlation between exam anxiety and exam performance. On further applying Pearson, actually Pearson correlation, full form is known as Pearson product moment correlation. Why we applied this? Because both of our variables were continuous or metric measurements. Applying Pearson product moment correlation, we found that there exists a negative and weak, negative and moderate correlation between, this is how you should report your result, between exam anxiety and exam performance. Here in bracket you can write R, which is a symbol for Spearman correlation, for Pearson correlation. R is equal to minus 44, minus 0.44. If exam anxiety is increased by 1 unit or 100%, then exam performance goes down by 0.441 units or 44.1%. This correlation is statistically significant because P is less than 0.05. Because here you can see P is equal to 0.000. So that is the overall interpretation of this Pearson correlation. Now, this we have applied because we were having both of our variables as continuous or metric variables. Means they were measured on a interval or a ratio scale. What if one of these variables is ordinal in nature, means categorical, and in that categorical, it is ordinal, it is ranked, then which test to apply? And in that case, you should not apply Pearson product moment correlation. You have to apply SPM correlation or Kendall tau correlation based on the situation. So for that matter, I want you to open a new file, correlation dataset 2. Can you see this? Yes, participants, can you see this?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
So here we will take two variables, creativity and position. And I'll tell you the story behind this. I have an assumption that those who are highly creative, particularly in telling stories, they turn out to be the better liars. They could tell better lies. Those who are highly creative, they can lie better as compared to others. So we ran a world's biggest liar competition. And in that competition, we invited 68 people. Now, these 68 people were asked to write a hypothetical story, a hypothetical situation, and then they were given marks on their creativity, how much they are creative in making a story. In that, we have measured their creativity. Based on their creativity score, we have given them a position in the competition. As you can see, first, third, fourth, second, and so on. So if a person is getting a particular score, he has been ranked first. If is getting a particular score, he has been ranked second, and so on. Again, I repeat, we asked 68 people to participate in a storytelling competition, and we gave them marks on their creativity of the story. The idea was to test a assumption or a hypothesis that those who are highly creative, they turn out to be better liars. So if a person is secure and based on their creativity scores from the story, we ranked them, we ranked them first, second, third, or fourth. Like that is their position in the competition. So a person getting first position means he is a better liar. Now, if you see, creativity score is the continuous measurement, whereas the position in the exam in the competition based on the creativity score is the ordinal rank, means categorical measurement. We want to test, is there any association between the creativity and position? And ultimately, what we want to test, that if a person is more creative, whether he turns out to be a better liar or not. Where the better liar is judged by their position in the competition, and their creativity is a score based on the story that they wrote, the hypothetical story. Is the situation clear? On one hand side, we have a continuous measurement called creativity. On the other hand side, we have a ordinal rank position. Positions are always ordinal in nature. This is ranking. So one of our variable is categorical, and that is the position in the competition. And that too, in categorical, it is ordinal rank. So to test the association or correlation between the creativity and position in the competition, we cannot apply Pearson correlation here because one of them is ordinal. So we will apply Spearman correlation. The method will be the same: analyze, correlate, bivariate, take creativity and position, and here you select Spearman and click on OK. Now see this result. Again, there is a moderate negative correlation between the creativity and position in the best liar competition. So if we have to write, how will we write? Test the correlation. What was the hypothesis? First, let's write the hypothesis. Creativity measured by the score.
Excuse me, sir. अगर ये pathway repeat for the second time, analyze step
Correct?
by step. Sir, if you repeat the pathway, analyze, then click on the correlation, and then this step, I
Okay,
missed
okay,
out. Yeah.
okay. You go to analyze, correlate, bivariate, select your variables creativity and position, and from here you select Spearman and click OK. Is that clear?
Yes, sir.
Yes, sir. Yes.
Okay.
Thank you.
Okay. And why we are applying? The method will remain the same. Instead of Pearson, we will apply Spearman. Why? Because one of our variable is ordinal. Let's see. Creativity is the continuous measurement because it is measured by the score they got on the story they made. Then they were ranked. Ranking was done based on creativity score. And then we want to test those with less rank. Less rank means the number 1, 2, 3, like that. Here, don't assume less means that they are number 7 or 10. No, less rank means the value of the rank. Those with less rank, like 1 or 2, first or second in the competition, tends to be better liars. So we want to check the correlation between creativity, which is continuous or metric measurement, and position in the ordinal rank, non-metric or category, which is non-metric or category. In that case, we will apply Pearson, sorry, Spearman. So we conducted Spearman. It is also known as inter-class correlation. interclass correlation and found that there exists a moderately negative correlation between the creativity score and rank in the competition. Now, how much? 37.3%. If creativity score increases by 1 unit or 100%, the position goes down by 33.7 for 5.337 unit or 33.7%. This correlation is significant at 95% confidence interval because it is less than 0.0. Nothing here. Is less than 0.05, it's 0.002. So if a person is more creative, means if their creativity score increases, then the number, that is from third they will move to second or from second to first, like that. So if creativity is increased by 1 unit, their number rank in the competition decreases by 0.337 units. Or if creativity score increases by 100%, the position number goes down by 33.7%. Goes down means from second they will rank to first number. So this shows that highly creative people tend to be better liars because more they are creative, their rank in the competition, the rank number goes down, means it decreases from second to first. And somebody coming first in the competition means they are better liars. Is this clear?
Yes, sir.
Okay. Now, but in this test, there is one basic problem. And what is that problem? If you see the position, the ranks are tied. Many people have got the first rank based on their scores. Many people have got the second rank. Many people have got the third rank, fourth rank. Means ranks are tied. So if the ranks are tied, means see the situation is one will be your continuous variable, another one will be your categorical and ordinal rank variable. But if ranks are tied, means many people getting the same rank, then Spearman correlation is not the best solution. The best solution is Kendall-Tau correlation. Suppose if all were getting different ranks, means first, second, third, fourth, fifth, sixth, seven, eight, nine, 10, and so on till 68. Every individual is getting an individual rank. Then you should have applied Spearman correlation. Please remember, if one variable is uh, continuous in nature, another one is ordinal rank or categorical. In that category, it is ordinal in nature. Ordinal means rank, and many people are getting similar ranks. That is, ranks are tied. Then the choice should go to Kendall-Tau correlation. If every individual is getting an individual rank, let's say in a race, Two people cannot come first. Somebody will come first, somebody will come second. If 10 people are running a race, everybody will come first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. Everybody will score, will get individual rank. In that case, you should apply Spearman correlation to test the correlation. But if ranks are tied, then the better solution is Kendall Tau. Method remains the same. Analyze, correlate, bivariate, select your variables, and rather than Spearman, select Kendall Tau. Spearman is denoted by, I'll show you the symbol. Now you see this result also shows almost similar value, only little bit of difference. There it was 37.3%, here it is 30%. But still it's negative correlation and moderate correlation. So moderately negative correlation and significant. P is less than 0.8. Only thing you need to take care of while choosing whether you should apply Kendall Tau or you should apply Spearman when one of your variable is ordinary rank is to check that whether ranks are tied or they are individual ranks. If everybody is getting an individual rank, then you should go for Spearman correlation. If ranks are tied, means many people are getting similar ranks. Let's say marks in an examination, or in our case, the creativity score, and based on that, their ranks. If they are tied, many people getting the same rank, then you should go for Kendall Tau. Where R, here you can, in the first case, you can see that Pearson correlation is denoted by R, small r, Spearman by RHO, rho, we call it as Spearman rho, and Kendall Tau is denoted by this symbol. I'll just draw that symbol. Inverse J. J, the opposite mirror image of J is the Kendall Tau. So this is the Kendall Tau correlation. This is how we measure it. Is that clear?
And just I have a question that when should we apply the Pearson correlation? Can you please repeat once again?
See, if both of your variables are continuous in nature. Continuous, are you understanding?
Yes, sir.
Continuous means either they are taken on a which scale? I'll write here.
Not categorical, not categorical.
If both variables are first, let me give you the scales. That would be a better solution. See, there are nominal measurements, ordinal measurements, interval measurements, and ratio measurements. These first two are known as categorical measurements. Like questions like yes, no, male, female are nominal in nature. Ranks are ordinal in nature, like good, better, best. Okay, these are categorical or non-metric. And you should always keep this in mind, because whether you are running a regression or correlation or t-test or ANOVA, it all starts from what kind of measurement you are taking. These are continuous measurements. or metric. Now, please note this one. If both the variables, which variable among whom you are trying to find the relationship, if both the variables are continuous, continuous or metric, whatever you write, continuous or metric in nature means either they are taken on interval or they are taken on ratio scales. Then Pearson product moment correlation. If one of the variable is categorical and ordinal. Categorical could be nominal also. For nominal, I will tell you another test. If it is ordinal and ordinal rank, then see the situation that if ranks are tight, that is many observations getting the same rank. Okay? General. If ranks are individual, that is every observation has an unique and individual rank. Right? 10 people participated in the competition and they are getting ranks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No two people are getting the same rank. And individual rank, then here, also known as inter class. Is that clear?
Yes, sir. Thank you so much.
Fine. Now, if fourth situation, if one of the, that means at least one of the variables should be continuous. If both will be categorical, then we won't apply correlation. We apply chi-square test of association. I hope this has been covered or it will be covered by some other expert. If both are nominal or you can say both are categorical in nature, and in that categorical, if they are nominal or ordinal rank, if both the variables, then we apply chi-square test. But if one of them is continuous, another one is categorical, in that categorical it is ordinal rank, then either Kendall tau or Spearman correlation based on how the ranks have been put. If they are tied, then Kendall tau. If they are individual ranks, then Spearman. If both are continuous or metric, then Pearson. But if both the variables, if one of the variables is categorical, now I have told you the situation of nominal. Now, sorry, ordinal. Now, the another variable is categorical and nominal. Then, biserial or biserial correlation. Please keep in mind that in all the cases, at least one of the variable is continuous. So if both are continuous, Pearson. If one is ordinal, either conduct or Spearman. And if one is categorical and in that it is nominal, then biserial or point by C. Nominal here means dichotomous. Questions like yes, no, male, female. In that case, there should you should use biserial or point by C. Now, when to use biserial? If there is continuous dichotomy, then biserial. If there is three dichotomy, then biserial. Now, what is continuous dichotomy and what is discrete? See, you have two categories in your variables that makes it a dichotomous. But if there is some relationship, some connecting dot between those two categories, then we call it as continuous dichotomy. Cases are very less of continuous dichotomy. For example, situation like pass and fail. Let's say 40% is the passing mark. Somebody got 39.8% or 39%. He belongs to a category of fail. If somebody gets 40%, he belongs to a category of pass. Means passing by marginal marks means falling into the category of pass by a marginal number or belonging to the category of fail by a marginal number. Means there is a thin line of connection. For example, male, female. If you are factoring transgenders also, then that could be a case of continuous dichotomy. But in discrete dichotomy, both the categories are, they don't have any connection with each other. For example, living and dead. There is no medical term saying that somebody is half dead. Somebody might be in coma or unconsciousness, and we say that half dead, but medically it is not half dead. Medically it is live. If the organs are working, that means the person is living. So living dead, winner and loser. Somebody winning a race, somebody losing a race by more margins. Then in that case, this is the discrete dichotomy. Male, female. If you are not factoring in transgender, then again this is a discrete dichotomy. If you are bringing in some connecting point, so in practical life you will find very less cases of continuous dichotomy because continuous dichotomy is like a oxymoron. Means you are saying that there are two categories, different categories, but they have some connecting link between. Very rare cases. Like I said, in a population you want to study male, female, and transgender. These three, then you can say that there is a continuous dichotomy. But if you're saying that no, only my studies is related to males and females only, then that's a discrete dichotomy. So if your variable, one of the variable is categorical and nominal, then you have to decide on biserial and point biserial based on the type of dichotomy there. Like if you ask somebody to answer yes, no, then this is a discrete dichotomy. But if you say yes, no, and in between you put a scale, somewhat yes, somewhat no, though practically it's not feasible. But in that case, that is a continuous dichotomy. Is the concept of continuous and discrete dichotomy clear? Yes, participants?
Yes, sir.
So only thing, if you are getting confused, keep in mind that there are very rare cases of continuous dichotomy. Means you will be getting two groups which are unrelated to each other. And in that case, you have to apply point by serial correlation. For that, you can use the third data set, correlation data set 3. So here there is a time and gender. So time is spent out of home, time away from home in hours in a particular week, and gender of teenagers, where 1 represents male and 0 represents female. So let's see that whether gender is associated with time spent out of home. Now time is an interval variable, right? That is continuous, and this one is categorical. In that we have two categories, male and female. And this is a case of discrete dichotomy. There is no connecting link in between. Both are two different groups. And if you want to find out the correlation, that whether gender is correlated with time, then we will apply point by serial. There is no separate method in SPSS. You will select bivariate, select both. See, this symbol says that both are nominal. This says that it's a scale. So please keep this in mind. So time away from home and gender of teenager. Keep Pearson only. The reporting you will write like RPP, point by serial. Click on OK. And see that there is a positive correlation between gender and time spent. And there is a moderate correlation, 37.8%. Means if gender value increases, means if it increases from 0 to 1, then time spent away from home also increases. And here, please remember, 1 means males. So we can say that male tends to spend more time as compared to females. Means as the gender value moves from 0 to 1, the time spent away from home also increases. And that shows that gender has a moderate positive correlation. If the person is male, they spend more time away from home. To cross check it, we recoded it. The third variable is the record of this, means what was 1 is 0 and what was 0 is 1. And please remember here again we have recoded. Previously, in the previous variable, you can see 0 stands for female, 1 for male. And here now 0 stands for male and 1 for female. We have transposed it, recoded it. And if we use this and this to test the correlation, see what will happen. Bivariate, we will remove this one and we will take teenager gender recoded. Okay. And you can see that we are getting the same values, 37.8%, but negative correlation. That means if the gender value decreases from 1 to 0, time spent away from home increases. Or if the gender value increases from 0 to 1, time spent away from home decreases by 37.8%. And here, please remember, in this case, 0 stands for males and 1 for females because we have recorded. Even this result shows that male tends to spend more time because as the value decreases from 1 to 0, where here 0 stands for male, the time spent away from home increases because it's a negative correlation. They will move in the opposite direction. So in first case, when we have taken gender, male as 1, female as 0, that was a positive correlation. You can see the value remains the same, 37.8%. Means as the gender changes from 0 to 1, means from female to male. If a person is a male, the time spent away from home will increase for them. Means male spends more time as compared to females. This is the association. In second case, we have recoded the gender. Means we have put 0 as male and 1 as female. Now the inverse of that. Again, we have got the same value but a negative correlation, which shows that if the value of gender goes down from 1 to 0, time spent away from home will increase. Or if the value increases from 0 to 1, time spent away from home decreases. And here, please remember 0 stands for male and 1 for female. This result also shows that male tends to spend more time away from home as compared to their female counterparts. Is this clear?
Yes, sir.
Okay. I have given you the data sets for practice. You can use that for your practice. Now now the last correlation, that is partial correlation. What is partial correlation? For that, I will again take you to my first data set. We have taken exam, we have taken anxiety, and found that exam and anxiety are negatively correlated with each other. Means if anxiety increases, performance in exam decreases. But we have also a third variable, revision time. This is affecting the relationship between exam and anxiety. So whatever we are getting as a correlation between exam and anxiety might not be a very correct correlation because a third variable is affecting this relationship. For example, let's say I have taken 1 liter of water to boil on a gas stove, and I have put the gas stove on a temperature, let's say 100 degrees centigrade. And I'm saying that the time taken for the water to boil is 5 minutes. Then I increase the temperature to 200 degrees centigrade. And then I noted that the time taken for the water to boil decreased to 3 minutes. So what I can say from this relationship, that there is a negative correlation between temperature and time taken for the water to boil. As temperature increases, time taken for the water to boil decreases. But will this phenomenon, which I am saying, will be applicable to every situation whenever we are boiling a water? Or there will be some external variables affecting this relationship? Is this a true relationship? I said that yes, if you take 1 liter of water and increase temperature from 100 to 200 degrees centigrade, the time taken for water to boil will decrease by 2 minutes. Previously, it was taking 5 minutes. Now it will take 3 minutes. There is a negative correlation. But will this stand true in all the cases? What if I take 2 liters of water at 200 degrees centigrade? Will the time taken for the water to boil decrease by 2 minutes? Or it will take more time?
It will take more time if the water is more.
It will take more time. Second situation is, if I take water at room temperature and ice cooled water, will they take the same time to boil? There is 1 liter of ice cold water and 1 liter of water at room temperature. Will they take the same time or they will take different time?
Different, sir.
They will take different time.
Yeah.
So whatever correlation which I am trying to measure between the time taken for the water to boil and temperature, that should be standardized. Means these external variables which are affecting these relationship, these should be controlled. Means if you want to get correct correlation in all the cases, then and you are saying that yes, 1 liter of water at 200 degree takes only 3 minutes to boil, then it's in all the cases it should be 1 liter of water and water at room temperature. That means the initial temperature of the water, okay, the quantity of the water, all these have been controlled and standardized because these are the external variables affecting the relationship. So whenever you are trying to find a relationship and you are seeing that there is a third variable that is affecting the relationship between your two variables, then that variable needs to be controlled. And this kind of correlation is known as partial correlation. So for example, we already found that exam and anxiety are negatively correlated. But revision is something that is affecting this relationship. A person might be highly anxious. If he is highly anxious, his exam score should go down. But what he is doing, he is revising more and more also. And ultimately, despite having high anxiety, the exam score is better because they are revising also. And if you find out the relationship between revise and exam, you'll find there is a positive correlation. If you revise the performance and time spent revising, you'll find there is a positive correlation. See, time spent revising and performance means though anxiety affects negatively the performance, but when a person is revising, then the scores are improving. Means more the person he revises, better the exam performance is. So ultimately, what we are seeing that the relationship between exam and anxiety is being affected by a third variable, revision. If we want to find the correct correlation between exam and anxiety, then we need to standardize this revision time or control this revision time. This kind of correlation is known as partial correlation. So go to analyze, correlate, and instead of bivariate, select partial. Now select exam performance, exam anxiety, and control for time spent. When do we do that? When we have a third variable or a fourth variable present in our study, and we believe that this variable is affecting the relationship between our two main variables. Then we control that variable. And such kind of correlation is known as partial correlation. Click on OK. I repeat this step, analyze, correlate, rather than bivariate. Now you don't have two variables, you have a third variable also. Go to partial, put your main variables here, and the variable, external variable that you believe is affecting the relationship should be controlled here, controlling for, click on OK. And you will get this result. So what you, now please see. What was the relationship between exam anxiety and performance previously? 44.1% negative correlation, right? Isn't it? See the first result. When we measured
Yes,
only the relation, huh?
Yes, sir. It's okay.
It was 44.1% negative correlation. When we controlled the time spent revising, can you see the correlation decreased? Now if you control for this time spent revising, then the relationship between performance and anxiety became a weak correlation, minus 24.7%. So if you control the time spent revising, if you standardize this variable, then the relationship between exam anxiety and performance, though it is negative, but it will be a weak correlation. Now, exam anxiety will only affect exam performance to a level of 24.7% when revision is controlled. Initially, it was 44.1%. 1%. So if there is a third variable which is affecting the relationship between your main variable, you should do a partial correlation by keeping that variable as the third variable as a control variable. And then you will get the better results of correlation. So now we can say that when we control the time spent revising, then the actual correlation between exam performance and exam anxiety is negative, weak correlation, and the correlation level is 24.7%. Initially, it was 44.1%. And statistically significant also, because see, the p-value is 0.012, which is less than 0.05. Is this clear?
Sir, how many variables can we control for? We cannot add a lot of variables, right?
No, you can control for as many variables you want. See, if you see, analyze, correlate, bivariate, sorry. Let's say if I want to control gender also, right? I can do that also. See, whatever the variables are that you believe that they are effective. See, I have just taken gender for illustration purpose, but ideally speaking, gender won't affect the exam performance and anxiety. But if you believe that, yes, and your literature review suggests, see, from where this belief is coming? This belief is coming from literature. So if you see any study, they will say that if a person revises more despite anxiety, their performance will that will affect their performance. More and more practice will affect the performance. So I want to find out the correct correlation between performance and anxiety. So in that case, the time spent revising needs to be controlled. If there is another variable, let's say IQ level, person might be highly anxious, that would affect their performance, but IQ level also has a role to play in the performance. And I want to find only relationship between anxiety and performance. Then I will control both the time spent revising and the IQ level. Or if I want to see the exam performance and exam anxiety correlation, and there is another one more variable, that is the course taught by two different teachers. Of course, their understanding level will be different. Then in that case, I have to control that also. So you have to choose really meticulously that which of the variable is actually affecting this relationship. Might be all variables in the study might not be affecting. There will be few. And in that few, you have to choose which are the most prominent ones. And this you can do only by literature review. When a lot of studies have indicated towards a particular variable affecting a relationship, you can control that variable.
Okay, sir, thank you.
It's up to you, but see, this is a software. You will put 10 variables, it will give you the results by controlling all those 10 variables. But the thing is, here you have to apply your own knowledge, your own mind, that which variable, because choosing a variable is a very means, critical step in designing a research. Whenever we design a research, we should identify our variables very meticulously. And that choice should come from a very strong literature review. That's why I always say that in any research, literature review is of prime importance. Or if it's experimental study, then what previous studies have found, you have to take that also. Means choose your variable based on the past studies. Is that okay?
Yes, sir, thank you.
Okay, so this was all about different type of correlations. Now we will move on to regression analysis. If you wish, can we have a 2 minutes of break?
Yes, sir. Yes,
Thank
sir.
you. Thank you. Thank you. We'll
Okay,
be back
sir.
within 2 minutes.
Okay, sir.
Sir, may I ask a question?
Yes, please.
So while performing correlation, if in case we are not performing this Pearson one, and
Mhm.
then we have one of the data which is categorical data in the form of yes or no, dichotomous data.
Means both your variable, both the variables.
No, sir. One
Huh.
variable will be continuous,
Huh.
another variable will be dichotomous, and
Okay.
controlled variable will be continuous. So
Okay.
two,
Then yeah,
yes, sir.
you can apply the same point by serial correlation while controlling. You should go to the partial correlation. Okay.
Yes, sir.
You are
Yes, sir.
saying one is yes, no, another one is this. Yes, then you can take those two, the yes, no, and your continuous variable in the main variables, and the third variable as the control variable,
Okay, so the
and
type of
and report that this was the point by serial correlation while controlling for, means this is a mixed method of point by serial as well as a partial correlation where you have controlled the third variable while finding out the relationship between your categorical variable and continuous variable.
so please it will be a combination of point by serial and
And control and a partial correlation means you have applied a partial point by serial, we term it as partial point by serial correlation.
okay. Thank you so much, sir. Thank you.
Yeah. So now moving on to regression analysis. Am I audible? Yes, audience, just let me know. Am I audible?
Yes, sir. Yes.
Okay. Thanks. Okay. Now we will move on to the predictive analytics technique, that is a regression analysis. Now, what is this regression? This regression is a predictive analytic technique and it is a hypothetical model of the relationship between two or more variables. And the model that we used here is linear, means there is a linear association between the variables. The two variables are, here I won't refer to as independent or dependent. I will say outcome variable y and predictor variable x. So when there is a linear association between x and y, means they can be fitted on a straight line. And you want to predict the value of y based on the value of x, where y is your outcome variable and x is the predictor variable. You can take it as dependent or independent, but I choose, when I talk of regression, then I choose to, or prefer to say y as outcome variable and x as predictor variable, because x is used to predict the future value of y. Then there is a thumb rule in statistics. Please do remember that every outcome that is y is equal to model plus error, where this model is the statistical model. It could be a t-test, ANOVA, correlation, or regression. When we talk of regression, then this outcome y is equal to, in place of model, b0 plus bx plus the error term e. Why we are factoring in the error term? Because nothing could be explained to the level of 100%. If based on various variables, if I could have been able to predict, I have learned taught a lot about regression analysis and many other predictive techniques. Being a data scientist, I have developed my own algorithms, but I have never been able to develop any algorithm, and nobody in this world which can predict anything to a level of 100%. Because if I could make a model which could predict anything to a level of 100%, just consider the situation. Based on daily stock prices, moving averages, candlesticks, and all these things, if I could be able to accurately predict the stock price, I could have been the richest person in this world. I would not have been an academician, right? Nothing could be explained to a level of 100%. So whatever goes as unexplained is due to this error term, because every data has some error terms. Now, what is this B0 and what is this Bx? This B0 is known as the intercept, and it's a constant value. It is used to predict the value of y, even if your x, that is your predictor variable, value is 0. Because let's say if x is equal to 0, then bx is equal to 0 and y is equal to 0. But if you put in this B0, then it can predict the value of y even if x is 0, because this B0 will be having some value. Let's say 1.3 plus x is equal to 0, bx will be 0, b into 0 is equal to 0. So again, the value of y will be 1.3. So this could be used to explain the value of y even if x is equal to 0. It is the intercept. And if you plot a straight line on x and y axis, the point where this straight line touches the y axis, that is known as this intercept. If you visualize this linear model, and that's why we call regression as a linear model. If there is a non-linear association, then there is another regression known as non-linear regression. We have Bayesian method, and there are a lot of. But generally talking, we are talking of linear regression. So if there is a linear association, means you are plotting the entire equation on a straight line, and the point where this straight line touches the y-axis or intersects the y-axis, that is known as the intercept or B0. Then B is the gradient or slope in that visualization. Or you can also say that it is the regression coefficient of the value x. And E is, of course, a error. So just again, y is your outcome which you want to measure. For that, you have made a predictive model, which is B0 plus Bx. If you have many x, then y will be, if you have many variables, then y. This is the case of simple linear regression. Simple linear regression. If you have many x, then y is equal to B0 plus B1 x1 plus B2 x2 and so on to Bn xn plus error. This is the case of multiple linear regression. There is no much difference between simple linear regression and multiple linear regression, except if you are predicting y based on one predictor variable, it is known as simple linear regression. If there are multiple predictors, many predictors, then that is known as multiple linear regression. And in case of multiple linear regression, there are few assumptions which should be followed by the data to apply the regression model. Otherwise, you should not. It is not at our whims and fancies that we can apply a linear regression. Ideally, for a linear regression, your x and y, ideally I'm saying, both should be continuous or metric measurements. However, you can take categorical measurements, but the model will not be that much explainable. And if your y, in case if your y is categorical, I'm saying this multiple or simple linear regression will only apply when both of your variable ideally are continuous. If let's say your x is categorical and y is continuous, then there is another linear model and we call it ANOVA. Actually, ANOVA is nothing but it's a generalized linear model. Similarly, we have 5 kinds of generalized linear model. One-way ANOVA, two-way ANOVA, ANCOVA, repeated measures ANOVA, and mixed ANOVA. So GLM 1 to 5. Let's say y is continuous and x is categorical, then another form of linear model known as ANOVA should be. And based on the data, you can decide whether it's an OR, or repeated regression. If your X is continuous, but Y is categorical, then that calls for application of logistic regression or classification techniques like logistic regression or the discriminant analysis or artificial neural networks or support vector machine. And there are many other machine learning models which you can. Even this multiple regression is one kind of machine learning model, what we call as supervised machine learning model. There are two kinds of machine learning models, supervised and unsupervised. In nutshell, supervised machine learning model is a model where in the algorithm, the data is fed in a particular pattern. There is a pattern of data. In unsupervised machine learning, the machine picks up the pattern by itself. It learns by itself. We need not to feed a set data pattern in the machine or the algorithm. So this regression, linear regression, be it simple or multiple, is a supervised machine learning model. And that's how I'm saying that both Y and X should be continuous in nature. So I have talked about this Y is equal to B0 plus Bx plus B. So the B is the regression coefficient or gradient or slope, and it shows the direction and or strength of the relationship. Negative means negative direction, positive means positive direction, and the value of B will be the regression coefficient. And B0 is the intercept and tells the value of Y when X is 0. And I told the point at which the regression line crosses the X-axis is known as the gradient, is known as the intercept. So here you can see that there are two regression lines touching at the same point, means same intercepts, but different gradients. Here you can see they are touching at different points. So they are this, but they are in moving in the same direction. So they are, so the B is same, that is the gradient is same, but intercept is different. It is just for illustration purpose. And this is the residual error, the error that I was talking about. All those data points which are away from, because whenever we talk of linear regression model, we talk of the fitting the model on a straight line. Any data point deviating from this straight line is the residual error. And residual error is actually the reason behind the explanation of the model or predictability of the model. If your model cannot be explained to a level of 100%, let's say if it is being explained to a level of 70%, then the remaining 30% is due to these residual errors because they are not fitting on the straight line. Data points above this straight line are known as positive residuals, and below this straight line are known as negative residuals. This is the basic concept of regression. Now there are few assumptions of regression that needs to be fulfilled. As I told, that choosing any statistical test is not at our whims and fancies. It should be, there should be some assumption that should be followed. So there should be linear association between X and Y. Tested true. How we tested the linear association? There should not be multi-collinearity on the predictors. You are taking only one predictor variable, then you need not take this. if you are taking many predictor variables, means if you are doing multiple regression, then you should test for multicollinearity. The concept of multicollinearity is that multicollinearity happens when your predictor variable, that is x, let's say you have three predictor variables x1, x2, and x3. If they are highly correlated with each other, then that creates a problem of multicollinearity. And initially, you can understand this multicollinearity when you are conducting reliability test for your data. In reliability analysis, if Cronbach alpha value is above 7.7, we say that the scale is reliable. But if it goes beyond the 0.9, let's say 0.93, 0.94, 0.95, then we should not be happy about it. Because if you plan to do regression, you will definitely get a problem of multicollinearity. Because the reliability concepts come from the concept of inter-item correlation. The Cronbach alpha value is nothing but the correlation value of all the statements that you have used in your question. And if they are highly correlated with each other, that will create the problem of multicollinearity. So let's say you have x1, x2, and x3. They are highly correlated with each other. What will happen? In a true situation, it might be a case that only x1 and x3 are able to predict y. x2 has nothing to do with the prediction of y, the second variable. But still, it is showing in the model that it is predicting y because it is borrowing its properties from either x1 or x3. And how it is borrowing the property? Because of high correlation with either x1 or x3. So let's say if x1, x2, and x3 are three variables, and x2 is highly correlated with x3, and that is the problem of multicollinearity. And where actually it will give you the problem, in fact, x2 is unable to explain why. But due to high correlation with x3, it is explaining why. So you will keep it into your model, and ultimately your model will be a false model. It won't be correct. So this multicollinearity issue needs to be addressed, and it is checked through VIF, variance integration factor, and PV, tolerance. Or no multicollinearity is desirable, IF should be less than 10 and tolerance value should be greater than 0.5. This is the thumb rule, please keep in mind. If VIF between 1 to 3, then no problem of multicollinearity at all. Up to 5, stable. Above 5, some problem. 10 and greater, serious problem of multicollinearity. Then, if the data is in series data, then there should be no auto correlation. Again, this is the kind of correlation, but in time series data, where auto correlation is a problem where one time series predicts another time series due to high correlation. What is this problem? Let's say you have a monthly stock performance of any equity for the year 2022. You have monthly stock performance of the same equity for the year 2021. Based on these 2 year data, you want to predict the performance of this particular equity in the year 2023. Now let's assume that 2021 data and 2022 data are highly correlated with each other. Then you won't be able to tell that whether 2023 prediction is coming from the data of 2021 or 2022. Means both time series data should not be correlated with each other, highly correlated with each other. This is tested through Irvin Watson test. Range should be between 0 to 4. If any autocorrelation range is beyond 0 and 4, this is the admissible limit. If it is less than 0 or more than 4, then it shows, if Darwin Watson statistic is coming as such, then it is said that there is a problem of autocorrelation. Fourth one is there should be normality of residual errors. The residual errors that I showed you, they should be normally distributed. In this case, we don't test for the normality of the data, we test for the normality of residual errors. So this can be tested in SPSS by, this is a multivariate normality. Normal, this quantile plots or normal PP. Probability. I don't know in the current version the statistical method is available, because these are visualization methods. The numerical method is available or not. There is the numerical method. We should, since if you are doing a multivariate test, then don't try to test it through univariate normality like Shapiro-Wilk or Kolmogorov-Smirnov. It's a multivariate, so try to test multivariate normality. So the numerical method is Anderson-Darling test. Darling test. It is available in R as of now. I'm not sure about the latest version of. But still you can do through normal quantile plots or PP plots. So these 4 things should be kept in mind. If any of this is violated, then your regression model is not correct. Now let's do a regression analysis. So this regression data set you can open, and you can see that there are 4 variables. The first one is advertising budget in thousands of pounds. Sales in thousands, means these are units, so each is in thousands. This is the number of time. Let me tell you the background. What is the background of this? There is a music album company owner. He has the advertising spent for 200 albums. The sales of the album data, number of time a particular album was played on a radio, the particular song was played on a radio, and the attractiveness or the popularity of the music band that have created that music album based on a scale of 1 to 10. So you could see that this attractiveness, number of plays on radio, and advertising budget, means amount spent on advertising. These three are predictor variables. And then he has sales data. Based on these 200 data, he wants to predict the future sales. And you can see that all are continuous variable. This is, and whenever we do regression, we should try to take measurements on ratio. Ratio scale is the highest level of measurement. And for structural equation modeling, for regression, means this is one of the best measurement that you can have. So this is data taken on a ratio scale. This is again ratio scale. This is the interval scale, and this is the interval scale. Based on these, he wants to predict sales. So the solution is a regression and multiple regression. But before going for multiple regression, let's check the first assumption, that is of linearity. Did I mention there should be linear association? Yes. So go to analyze, graph, legacy dialogues, scatter plot, define on the y-axis your sales will be there. Take advertising budget on x-axis. Okay. Fit to a straight line, and you can see there is a linear association. And apart from this, this R square tells you that if taken alone, advertising budget can explain the album sale to a level of 33.5%. Then do the same thing for number of plays on radio, fit line at total. Here, again, there is a linear association, and alone, if taken alone, number of plays on radio can predict the album sales to a level of 35.9%. When taken alone, as of now, I'm not taking as it is. All in total, I'm taking alone. Then do it for the third variable. Define. And let's take attractiveness of the band. There is a very little linear association and lot of residual errors here. And due to that only, you can see there are many data points lying above and below this straight line, deviating from the straight line. These are, with the third variable, there are lot of residual errors. And due to this, you can see that alone the attractiveness of the band can predict album sales only to a level of 10.6%. But let's check what if we take this in all together in a model. So go to analyze, regression, and linear. Take album sales as your dependent variable. Now here comes the method which most of us avoid or forget. By default, it is enter method. Which method of regression you should choose is very important. If you are choosing enter method, we also call it as forced entry method. Means you are allowing the software to choose, because whenever regression happens, it doesn't happen simultaneously. The software or the algorithm, be whatever you use, R, Python, or even you use Excel, or you make your own model, the algorithm is such that first it regresses that predictor variable that is explaining maximum variance. And you are allowing a machine to do this. So first it will check X1, from X1, X2, and X3. it will check which one is explaining maximum variance. Let's say it found that X3 is explaining almost 60% of the variance. So it will first regress with X3. Then remaining 40, it is saying that, okay, X2 is explaining out of remaining 40%, X2 is explaining 30%. Then in the middle, it will put X2 in the second order. And then it will put X1 as the last. This might be correct or this might not be correct. Let me illustrate you this with an example. There is a cold weather outside. You have a jacket, you have a pair of shirts, you have a pair of trousers, a shirt, a socks, and shoe. And now you are asking machine to tell you in which order you should wear all this so that you can be prevented from cold. So it will check for the maximum variance. So it will say that if you should wear jacket first because that explains maximum variance. That will protect you maximum from cold. Then it will ask you to wear your shirt over your jacket. Then it will ask you to wear your trousers. Then it will ask you to wear your shoes and then socks over the shoes. Ultimately, you'll be saved from cold. But is this a good fit that you wear shirt over a jacket? No. So similar problem happens when you are using the forced entry method. This method should be used only when you are not sure that which of the variable will affect your outcome variable the most. And that's where, so two things you should keep in mind. Choosing the proper method of regression and choosing the variable. To explain any outcome, there could be hundreds of variables. But is it worth taking all those variables? In our case, album sales can be predicted by advertising budget, means how much is spent on advertising, how many times the song has been played on the radio, what is the popularity of the music album band, let's say Palace and Euphoria or Justin Bieber have created some album, music album. Chances of it being sold will be high because they are popular bands. This makes sense. But cost of producing album is another variable. Is it a good fit or good variable to be taken into account for predicting album sales? Not at all. Not at all. It could be a variable, but it is not that much important. So you should choose only those variables which are very important. And how? Again, the literature. From literature review, if you come to know, many studies are indicating that yes, these are the variables which will be affecting maximum. Then you choose those variables first and the other variable later on. That is known as step-by-step method, and the extension of step-by-step method are removed backward and forward. So let's say I will choose, because well, enter method or forced entry should only be used when you are not sure that whether your variables in which order they will affect the outcome. So let's say I am pretty sure because I know that there is a direct linkage between advertising and album sales. More advertising leads to more sales. Many of the studies have established this. So I will put this first. The moment I am choosing this stepwise method, here the next. This is known as hierarchical regression. Actually, the method is known as hierarchical regression. In the next step, I have to choose the remaining two. If I'm sure that, okay, the second variable of importance is airplay, then I will choose it here and move on to the third and choose the third in the third step. But here I'm not sure about the number of plays and attractiveness. I haven't found much studies related to this. So I will choose this together in this method. Or if I'm sure, then I can choose one by one. So as of now, I am doing this regression in two steps. In the first step, I am regressing advertising budget on album sales, and in the second method, I am putting number of plays and attractiveness of band together. If I'm not sure, then I should have put all three in first. But again, the problem of enter method that I have told that will be here. Go to statistics. Yes, model R. Since I'm doing in multiple steps, two steps, so R square change I want. Multi-collinearity problem could be checked through collinearity diagnostics. Then Durbin-Watson, though it's not a time series data, but to show you how it works, I will choose Durbin-Watson also for autocorrelation. Plots for normality plot of residuals. So jet residuals and standardized residuals. I will produce all partial. So I will select histogram and normal probability, PP plot. Continue. Save. As of now, I'm avoiding this. If I don't want to save it for further analysis, other thing remains the same, click OK. Now see your model summary. In the first model, what we did, see, this is the model. In first, we took only advertising budget. Okay. And in the second step, we took advertising, attractiveness of the band, and number of plays on the radio. None of the variables were removed because all were found to be significantly affecting the outcome. Now, if you see the R square change, which is the level of variance explained. So alone, advertising budget is explaining 33.5%. Means it is predicting the sales of album to a level of 33.5%. And if you see here, when we have plotted this scatter plot, alone I have told you that advertising budget can explain album sales to a level of 33.5%. The same result you get. Anyways, when we added two more variables in the second step, our R square improved from 33.5% to now 66.5%. So this is our final value, which we should take. So this is the R square, which tells you about the predictability, the variance explained. Then a question comes, what is the role of adjusted R square? Should we report R square or adjusted R square? To tell about how much the variance can be explained, we should use R square. Adjusted R square is used to cross-validate the model. If there is no much difference between R square and adjusted R square, then we can say that the model is cross-validated. Because when you are developing a predictive model, you are predicting here on the basis of sample, where our sample size was 200. Whether this model can be used in the population or not, because our aim, whenever we are making a predictive model, our aim is that the data from the sample on which the model has been built, that model should be generalizable to the population also. Given in any case, if we take the value of album advertising budget, number of plays on the radio, and popularity of the band, in any case, it should explain the same level, that is 66.5%. If there is high difference between R square and adjusted R square, then the model is not cross-validated, and you should check your data. So as of now, our model is cross-validated, and this is checked by adjusted R square. There should not be much difference between R square and adjusted R square. So we will take the second model where we are putting all three. So 66.5% is the predictability of the model. Model is cross-validated. Then you come to this Durbin-Watson. It is in the range between 0 to 4, 1.95. So there is no problem of multi-collinearity. Then there is ANOVA table also, because I told ANOVA is a generalized linear model. What does this ANOVA do? This tells you about the fitness of the model, whether the model is a good fit or not. So F value, the Friedman value, should be greater than 1 and should be significant. Because we are taking the second model, so we will take the value of second model. Even in case of first model also, it was greater than 1, but we will take this one because we are taking the second model, which have shown the improve in the R square value. So F is 129 or near to 1, yes, 129, and significant, P is less than 0.05. Means our model is a good fit. But what is the model? So that again, the model is, your model is, see, album sales Y is equal to, now take the B0, that is the constant, this value, minus 26.613 plus B1 0.085 to X1 advertising budget plus B2 3.367 into airplay plus B3 attractiveness of the band and the regression coefficient to 11.086 into, this is our entire predictive model. So in this equation, if you put the value of advertising budget, the value of number of time that particular song was played on the radio, and the attractiveness of the band, you will get the actual value of, you can predict how many albums could be sold. But please remember, this predictability is only 66.5%. The remaining 33.5% goes unexplained due to residual errors. Okay, so 66.5% is also a good predictability. And what does these values tell you? That if advertising budget is increased by 1 per unit, it yields an increase of 0.085, and since it is in units of 1,000 of units, means multiplied by 1,000. So 1,000 pound spent, because 1 unit is in 1,000 pounds. So 1,000 pound spent leads to 85 albums sold. One more time the song is played on the radio leads to 3,367 albums sold. And if the attractiveness of the band is increased by one more time, means if there is a band which is popular on a scale of 10, let's say 7 is the popularity. If you take a band to create the album which has a popularity of 8, means 1 unit increase in the popularity, that will yield 11,086 albums sold individually. In total, you put all these values, let's say whatever value you have for advertising budget, or whatever value you have for airplay, whatever value you have for attractiveness, you put into this equation, you will find the number of albums sold, but predictability is at the level of 66.5%. Coming to linearity, we have already checked. No problem of autocorrelation is there. Your model is cross-validated. Model is a good fit given by F value and its significance. Now multi-collinearity. See, the tolerance value should be greater than 0.2, which is greater in all the cases. It ranges from, see here, 0.986, 0.959, 0.963 for all the 3 variables. VIF 1.015 for advertising budget, 1.043 for number of plays on radio, 1.038 for attractiveness of the band, means it is between 1 to 3 very acceptable, means there is no problem of multicollinearity at all. Now the last, normality of residual errors. If you see this histogram, you can see a bell-shaped curve, almost there is normality. Now how to interpret this normal PP plot? If these data points are close to the straight line and the first half is in symmetry with the second half, means they show a symmetry, then you can say that there is a normality of residual errors. So you can see that most of the data points are lying on this straight line. first half symmetry and the down lower half symmetry is almost the same. They are symmetrical. That means there is with both method means here also and here also you can say that the data is residuals are normally distributed. So overall, all the assumptions of regression are fulfilled. You got your regression model also. You got the predictability level of your model, and your model is the good fit and cross-validated. So this is all about regression. Now, questions if any, I am ready to take it up.
Sir,